So here's an example to warm up your conceptual muscles. Look at a market in which there are 100 consumers, each with WI2, with a wealth of or endowment of 2 units of good M. That's what they bring to the market. And suppose that there is only one firm with a cost function that has the following features. There is a semi-fixed cost of 100, and the marginal cost is fixed to $1 per unit, and this is dollars. Sorry, dollars per unit. And then I want you to plot the set of feasible symmetric allocations. And what I mean by symmetric is allocations in which every consumer is treated in the same way. Symmetric means everybody's treated the same way. In this case, because there is only one firm, it will automatically be symmetric for the firms. But I want only you to consider allocations in which the consumers are treated in the same way. Now, how do we solve this problem? First, let me remind you of one quick thing, that the technology for this firm means that it has a cost function that looks like this. So if these are this is the amount that it wants to produce, Q, and this is the cost, the total cost, it basically here, if he wants to produce 0, it pays 0. If he wants to produce every a little bit, it has to pay the semi-fixed cost, and then it increases. This point is empty, this point is full. It increases at a constant slope of 1. That's what that cost function looks like. So given that, let's try to characterize what the set of symmetric allocations look like. So one possibility is that we don't produce anything, so we are producing at this point, and therefore no good, so this is going to be how much they consume of good M, how much they consume of good X. There is no production of good X, therefore everything gets consumed in good M. Since there are 100 consumers, each with a wealth of 2, at a symmetric allocation, everybody gets the same amount. And what we have is that this at 2 is a feasible point. Okay? Now, suppose that the consumers instead want to consume a little bit, just even a tiny bit of good Q. Then that has to be produced. That means that the semi-fixed costs, which are equal to 100, need to be paid. So the first thing we need to pay is 100. That means in a symmetric allocation, every consumer pays 1. So that moves us to kind of 1 here, to this point there. But of course, we're going to want to consume a little bit of, we cannot just get that point, because at that point there's no production of X, so the semi-fixed costs are not paid. But what happens basically, just to make the story short, is that we get a line like this with that point open, in which after we pay the fixed cost, we can trade off at a rate of 1 to 1 however much we want to consume of good Q, because they can be produced at a constant slope of 1. So we get all of that line except for that point. That, with that point open, is the set of symmetric feasible allocations for this example. Please notice that we didn't write explicitly the equality constraints that are in the definition of a feasible allocation, but we have been using them in characterizing the solution set for symmetric allocations. How? Well, we always assume that whatever good M was not used was fully put into production, and that it translated into the amount of good X that was available for consumption based on this production function. So for example, when we decided to put all of the good M into production, we assumed that the first 100 units were used to pay the semi-fixed cost, and that after that, everything else were translated into good X at a marginal cost, constant marginal cost of 1. So implicitly, we are applying the definitions without having to write them explicitly to avoid the notation becoming cumbersome.